Welcome to the second presentation here at the AIMS MoIP showcase at AES New York 2022. Let me first note that unfortunately the original recording in New York did not succeed. That is why I had to re-record the whole presentation here at home in Munich. So let's jump into the topic. It's about timing and synchronization in AES67 and SMPTE ST 2110. And the subtitle is Why PTP is at the heart of your MoIP system. So my name is Andreas Hildebrand. I'm working for ALC Networks out of Munich, and we are the guys who invented, deployed Ravenna AoIP media technology to the world, basically. So let's jump into the topic. We can state a few general requirements when it comes to timing and synchronization in media over IP systems. First of all, we want to have full media bit transparency. That means that every signal I'm feeding into the system should be able to be played out unaltered at the other side of the system. So we definitely want to avoid any sample rate conversion, and that in turn means that all streams on a network or all devices on a network need to use the same media clock. And that basically means the media clock is the sampling rate, and that is the same for input devices or ingest devices as well as playout devices. Of course, I don't want to be restricted to just one sample rate for the whole network. I want to be able to use different sample rates, also different media like audio and video on the same network. So then the solution, the technology needs to support different media clocks or sample rates on the same network at the same time. Another very important requirement is that I definitely want to have a determinable and most possibly also a very low end-to-end latency between input and output. And if I have a determinable end-to-end latency, I will also care about time alignment between media streams so that I can have sample accurately aligned playout between any two or even more streams, the same or different places in the network. And then, of course, since I already have a network in place, I want to get rid of the house clock distribution, usually the green wire you're running around your facility carrying a word clock or black burst or any other genlock signal. So from these general requirements, there are some clear indications. First of all, we can tell that clock reassembly from stream data is not applicable. That's the asynchronous case where I feed a signal into the system and the receiver needs to regenerate the input media clock from the received signal. So the traditional one-to-one clock regeneration method. We call this the asynchronous operation mode. So that is definitely something which would not fulfill the requirements we have set forth. The next one is that the pure distribution of a master clock beat signal, like the house clock we were traditionally running around the facility, is also not sufficient because that has no means of time and would not be sufficient for aligning streams time-wise. So we would call this the synchronous operation mode. That is basically the case when we have the house clock running around the system, feeding a signal in and getting it out on the receiver side at the same pace, but we actually don't know how long it has been in the system and we don't have a fixed timing relationship. So we definitely need a common understanding of a reference time for the whole system, which sometimes is called the wall clock. And actually, if that is present, then this mode is called the synchronous operation. So we have asynchronous, synchronous, and synchronous operation. All right, so let's have a quick look at what various time synchronization methods have been made available over the years. First of all, there's quite an old scheme. It's called IRIG, which is the abbreviation for Inter-Range Instrumentation Group. That is basically a serial or pulse-based transmission of time, and it has its roots in military applications. It dates back in 1960, but it's still maintained. So as far as I know, the last version update or standard update has been published in 2016. The accuracy you can gain out of this is about 1 microsecond. Then there's another protocol you all are aware of, because that's how you adjust your clocks on your computers and PCs every day. That's the Network Time Protocol, which has been invented in 1985. And as far as the last revision is the version 4, which has been published in 2010. With NTP, you can get an accuracy as good as approximately 5 milliseconds if you are running your system on the internet or receiving your time through an internet-based servers. If you're supplying local NTP servers in your system, accuracy can get below 1 millisecond as a local network. Then there's another protocol or method being released for wireless communication methods, like the 801.11, which is the WLAN, the wireless local area network. The RBS or RBIS method, which is reference broadcast synchronization, reference broadcast infrastructure synchronization. That has been defined in 2002 and has received its last update in 2012. And that accuracy you can get out of is about 5 microseconds. Next one we're looking at is Precision Time Protocol, IEEE 1588. Has been published in its first version, or its first release, in 2002. Then in 2008, there was a successor version, which is the version 2.0. And in 2019, the IEEE published the version 2.1. And the accuracy you can get out of PTP, even in its original version, is approximately down to 20 nanoseconds, and even better if you look at the version 2.1. Of course, always depending on certain network scenarios. And then there's the almighty global navigation satellite system on top of us, most commonly known as GPS, Global Positioning System. So again, that satellite base has been introduced in 2008 and received some latest standard updates in 2015. And the accuracy we can get out of a GPS or any other GNSS system is even better than with PTP. It's going all the way down to 2 nanoseconds and maybe even below. Okay, so now that we know what methods are available and what accuracy can get out of it, let's have a look at the particular requirements, accuracy requirements of media over IP systems. And the first thing we need to state is that audio applications have the highest time accuracy and precision demands. Might be surprising for the video guys, but actually audio has much higher accuracy and precision demands when it comes to timing. Let's look at the first requirement, one which applies to alignment of streams. If I want to sample accurately aligned streams, that means that my time, the whole network, is not allowed to deviate more than plus minus half a sample. So how is this? Let's see, we have a transmitter and we have a sample period here. So a particular sample falls into that sample period. We have a receiver, let's say the first receiver, which may have a media clock which is off by half a cycle. So that means that the first sample of that sampling period aligns with the rising edge of that particular media clock. And let's assume we have another receiver, receiver 2, which is a bit upfront the original media clock. So that has a phase shift of minus half a phase period or sample period here. So in total, the difference between receiver 1 and receiver 2 is less, or at maximum 1 phase. And that is the requirement we actually need, 1 phase period. That is the requirement we actually need in order to sample accurately align playouts. So if we have a deviation, a phase deviation, which is larger than 1 period, we cannot perfectly align matching samples for a playout. The next thing we need to understand is what are the accuracy requirements following from this. So at 48 kilohertz, that means half a sample period is about plus minus 10 microsecond. At 96 kilohertz, that's already half of it. And we go up to 192 kilohertz. We need an accuracy requirement of plus minus 5 microseconds with respect to the reference time. Now we have a second requirement, and that is if we want to distribute a word clock reference throughout the system, we have another standard for that, and that is AES11, and that calls for a ±5% maximum jitter or wonder with respect to the master clock or to the clock within itself, actually. So if we look at that one, we have a transmitter and a receiver, and we want to rebuild the master clock of the transmitter, media clock of the transmitter, with the same clock as same clock at the receiver side. We are not allowed to have a deviation of ±5% of the phase accuracy of the transmitter. All right, so in numbers, that 48 kilohertz, this is ±1 microsecond. At 96 kilohertz, we have ±500 nanoseconds, and 192 kilohertz, that is already down to ±250 nanosecond for the maximum allowed tolerance among any two devices on the network. All right, so let's again have a look at the table, and if we compare the table with our just defined requirements, we can see that only PTP is capable of delivering the required accuracy, while of course any GNS system is also capable of delivering this accuracy, but you definitely don't want to supply a GPS receiver with each individual device. So PTP as a network-based time distribution protocol is absolutely suitable for fulfilling our requirements. Well, basically, that already gives you the answer why we have PTP at the heart of our system. Well, let's look a bit further. First of all, some fun facts here. We have, meanwhile, we have some synchronization mechanisms which allow even better accuracy below 1 nanosecond, or pure software-based methods or algorithms which can run without hardware support and achieve 25 nanoseconds based on pure software. That is a very suitable scheme for example, for virtualized environments, which are getting more and more popular. Don't want to highlight on these, but want to look into PTP and how we actually now generate media clocks and synchronization and our alignment out of PTP. So first of all, PTP is a standard published by the IEEE. It's a precision time protocol. It has this number IEEE 1588. It allows accurate sub-microsecond time and frequency transfer. It's a highly generic standard, so it hasn't been invented for media, but it originates actually from the industrial automation and the measurement industry. It also allows for customizable profiles, which basically tell the system at what message rate it has to operate and many other things in order to fulfill the particular requirements of any particular application. So that's the reason why it has been, is already in use by a huge number of different industries like telecom, power, finance, test measurement, and so on. So I already mentioned that the first version has been published in 2002 as version 1. The most common version, which is currently being used, is the version 2, which has been published in 2008. The problem was that with the publishing of version 2, there was an incompatibility with version 1. So you were not able to run version 1 devices in a version 2 system. You had to choose between version 1 or version 2, and were not able to just mix systems with version 1 and version 2. And so that is the reason why with the latest revision, which has been published in 2019, version 2.1, IEEE made sure that this now is fully backward compatible. So any version 2.1 device, be it Grandmaster or EndNote, can also successfully interoperate with the pure version 2 implementation. So since PTP, the way it works, the algorithms, the methods, the function, and so on have been introduced in other places numerous times. I'll jump over how PTP actually works. And we are looking into how we actually get synchronization and generate media clocks for our purposes in media over IP systems. So first of all, we can say that all nodes are running local clocks. So any device has its own clock, its own frequency generator built in. And those local clocks are precisely synchronized to a common wall clock via PTP. So have a common wall clock system there, a grandmaster, if you can see in a minute. And PTP is being used to discipline all the local clocks time-wise. Now, if I have the same time in all the devices, I can generate whatever media clock I like locally in any of those devices. And I can be sure that if the time is only precise enough, I have the very same, mostly the same media clocks running at all devices. So here's an illustration how that works. We have a master clock somewhere in the facility that may or may not be referenced to GPS. It depends if we want to have a very high precision, or if we want to have a synchronization with other facilities sitting somewhere else in the region, or even as a matter of fact somewhere in the world, because it's a global timing system. Now this master clock distributes its time via PTP to all the connected slave clocks, to all the devices actually. So precision time protocol is used to adjust all the local independently running clocks to have the same time with the appropriate accuracy as the master clock. And once all these clocks show the same time, I can locally generate the media clocks independently, because if the time is accurately aligned, the media clocks will also be the same according to the time accuracy I can achieve in my local devices. So once I have the media clocks, I can also understand that the generation of any desired media clock sample rate is possible. I only would have to tell a particular device which media clock it had to generate, right? If I tell two devices to generate 48 kilohertz, they are absolutely generating the same 48 kilohertz, even phase aligned. If I tell another device to generate 44.1, it's generating 44.1 media clock cycles per second from synchronized time. Of course, 44.1 and 48 kilohertz devices cannot directly communicate with each other, but the benefit is the 44.1 clock devices have a stable relationship to all the other, let's say 48 or whatever media clock they are running on devices on the network at any time. So that makes it possible to have concurrent operation of different media clocks at the same time on the same network, even if, of course, 44.1 signal cannot be processed by a 48 kilohertz device. But I can run different 48 kilohertz streams, different 44.1 kilohertz streams. I can run video signals, which are usually running at a 90 kilohertz clock, all concurrently on the same network, all generating their media clocks from one reference time from the wall clock device. Now, the phase accuracy, the required phase accuracy set forth in AES11, remember 5% of the sample period, is achievable in most cases. Sometimes, or in larger networks, that means that I have to deploy so-called PTP-aware switches in the network that are basically standard switches which natively understand PTP messages and make sure that the accuracy or precision of the PTP timing is maintained and preserved even in larger networks, even through a number of hops I'm running those messages across. As mentioned before, the synchronization across facilities is possible if I reference the local grandmasters to absolute time. Absolute time means usually International Atomic Time, which is what's being served by GPS. So if I have a GPS referenced grandmaster in different locations, I can make sure that the time which is distributed with PTP locally in the local networks is absolutely the same at any point in time. Now, then the next step is, once I have time and once I have the aligned or identical media clocks being generated at any individual node, the next step is that with the sampling or generation of an audio sample or video frame, I have to timestamp the first sample in a packet, or any particular sample basically, with the related wall clock time. So essentially, every essence segment every essence fragment, which means an audio sample or video frame, gets an accurate timestamp which tells, which keeps connected to that particular frame or audio sample, and is able to tell any other participating device in the system when this particular sample had been generated. So every essence data receives a generation timestamp from local clock, which in turn is synchronized with the reference clock system. So let's have a closer look how this actually works. If we look a bit deeper, we actually have three types of clock in a complete system. That's the wall clock, which I already mentioned, which is provided by the grandmaster, and we have the local copy of the wall clock in each node, well, in the local clocks. Then from the local clocks, I can derive a media clock, which can be any sampling frequency I need or I like. And from that media clock, the RTP clock or the stream clock is directly derived. So let's have a quick look at a picture, because that is better than 1,000 words. We have a reference clock, a PTP grandmaster. We have a sender and a receiver. Just the simplicity, just one device of each type. We have the local clocks in the devices, and the local clocks are disciplined by PTP, so they show the same time as the grandmaster, such that the local clock and the sender and the local receiver are identical. I generate the media clocks locally. That means that the media clock derived in the sender or generated in the sender is the same as the media clock in the receiver. If I both set them to, let's say, nominally 48 kilohertz, I know that even if they are accurately measured, not exactly 48 kilohertz, but just 47.9999 something, they are absolutely the same because they follow the reference clock of the system. Now, with the media clock, I'm sampling my audio data and putting that into the data stream, actually, and that stream is being driven by the RTP stream clock, but the RTP stream clock in turn is directly related back to the media clock. It only carries a random offset per stream, and that is only because the underlying standard, the RC3550, which is the IETF standard for RTP, for real-time transport protocol, suggests to have a random offset per stream in order to defeat any crypto attack on the RTP streams if I'm using encrypted streams, because as we can see in a second, the offset is part of the encrypted RTP header, just in case I'm using, encrypted RTP streaming. However, it's of course vital that the offset I'm setting up for any individual stream remains constant for the lifetime of the stream. And of course, the receiver needs to know this value, otherwise it won't be able to correct for the random offset and align the stream with other streams. And so that is why the offset is being communicated to the receiver on an out-of-band channel, whatever that is. There are several protocols available. Most commonly, there's the RTSP protocol, where you can provide the SDP data, which also carries this media clock offset. There are manual means, there's NMOS. There are many, many different means and protocols how you can convey the SDP data, which also includes this media clock offset from the sender to the receiver. So once the receiver knows the offset, it can calculate for it and can perfectly align this stream again to its internal clock and in turn to other streams in the network. Now, this is the case for AES67 SMPTE put a constraint on this. They were looking at this random offset, and they found that since they are not using encrypted RTP at all, that this random offset doesn't make any sense for their purposes. And they said, okay, we mandate that all senders use a zero offset. So basically that all streams are directly tied to the reference clock and have no random offset against each other. So there is no need basically to communicate the media clock offset because it's always zero. That's a constraint 702110 has put forward in their papers. Now, how is all this coming together? Well, if we look in RTP packets, so RTP packets is what we call the layer 5. That RTP packet consists of an RTP header and an RTP payload The RTP header has 12 bytes overhead. The RTP payload area carries any number of up to 1,440 bytes of data, of audio data, or any other media data, actually. Actually, it would be 1,460 bytes if it comes to IP version 4, but since IP version 6 would only allow for 1,440 bytes, AES67 has already restricted or constrained the maximum payload size for 1,440 bytes. So now, if you look a bit closer to the RTP header, there's a timestamp field that is right here. And that timestamp field actually is 32 bits wide, and it's not carrying a time data in terms of absolute time of day. It is carrying a media clock counter when used with linear PCM audio, and that's what we're talking about here, right? So when we are transporting linear PCM audio, this timestamp actually indicates at which media clock counter a particular sample has been ingested. And the definition for AES67 as well as for SMPTE2110 is that the media clock counter starts at 0 at the origin of the PTP time domain, which is the 1st January of 1970. So the system is actually counting the number of media clock phases which have occurred since the 1st January of 1970. And whenever a particular sample is ingested now, it has a related media clock counter, and that value is actually being put into the timestamp field of the RTP header and travels with the accompanying data, where the first sample, if we're talking about audio, refers exactly to this particular media clock counter. So the receiver or any receiving device exactly knows when the first sample in the audio packet payload, RTP packet payload, had been generated with respect to media clock count values. Fun fact, at 48 kilohertz, we will have a rollover about once per day. Well, basically, it doesn't matter in our case because we are talking about real-time distribution, right? And in real time, that would only cause a problem if a stream is actually on its way for more than 24 hours before it's being received by a receiver. And that time, it can travel 3 times back and forth to Neptune, I guess. That's approximately the time it would require then. So no problem for us. We can stick with the media clock counter, and rollover is not a problem for us. So now that we have the generation point of time, we can also fix or determine a particular play out time, or what we call it in AES67 link offset, a play out delay, what we call it link offset in AES67. So let's quickly look how that link offset works and how the play out time is actually determined from that. We have a sender system. We have, say, an A to D converter where we have the sampling stage. The media clock drives the sampler, and all the samples go into a sender packet buffer until the desired number of samples per packet is reached, and then it sends the packet off to the network, right? And as you can see, the media clock is being directly derived from the PTP synchronized network clock. Of course, we have the very same thing in the receiver side of things. We receive packets, we unpack samples into the receiver buffer. We have a network clock synchronizing or generating the media clock, which drives then the output stage. And just for reference, because sometimes, well, IP network in between, of course. Yes, right. Sometimes with timestamps, people always think of 1588 timestamps. Well, these timestamps, the RTP timestamps, have nothing to do with the 1588 measurement planes and their respective timestamps. Unfortunately, it's the same word, but the timestamps in 1588 are means or part of the function or the method how I can actually achieve such an accurate time alignment between master and slave clock. But for our link offset and playout discussion, this is of no means at all. So I delete them from the picture again. And our reference time planes are the ingress time point, the egress time point, and between those is the link offset. So that means the time, the exact time when I sample, take a sample in or ingest a sample, and the time when I want to play out a sample or forward it to the next processing stage. That's called the link offset. These are our reference time planes. And so the calculation is quite easy. We have the RTP timestamp, which marks the first sample in a packet, media clock counter units. We add the desired or chosen link offset to it. We may have eventually to calculate for the random media offset in case of AES67, SMPTE makes it a bit more easier. There's a 0 required here. And from that simple calculation, the receiver exactly knows what the desired play out time for this particular sample is. All right, so now that I have an exact play out time through the link offset, I'm also able to align any number of streams for play out, even in independent devices. I only have to play them out basically at the same time. So I have to observe the incoming timestamps and the desired link offset. And if I have the same link offset configured for any two devices, I will have the play out exactly the same time happening anywhere in the system. So let's have a quick look at the production workflow example, which makes it a bit more understandable. Let's say we have a camera feed which crosses a processing device and another processing device and is then to be displayed or played out on a display. And we have a microphone signal, an audio signal coming from a microphone running through a mixer, for example, and it's then designated for a loudspeaker. And it's immediately understandable that the time the signal would need to pass, the audio signal needs to pass through the chain until it reaches the speaker is shorter than the time of the video signal passing through its processing devices. So what actually needs to happen in the system, and I want to have aligned, let's say lip sync or even better aligned playout, is I would have to tell the speaker to hold up the playout for a while before, you know, the corresponding, or until the corresponding video signal reaches the screen or the video playout display. So it's basically that I both tell the system, the screen as well as the speaker, that the link offset matches the longest link offset for the video in this particular application. Of course, that might require a certain amount of buffer in the speaker device. Actually, all these devices have these type of buffers because they need to account for you know, packet jitter and other things which can occur in the network. This is a story of a different presentation coming up, I guess, tomorrow. And now the question, of course, is how do I establish all these link offsets and buffer configuration? And that usually is the task of a broadcast control system, which knows about the internal processing times of all these subsequent stages and can then dial in the desired link offsets actually to all the participating devices. And of course, the final link offset in the speaker, which will then make sure that we have a perfectly aligned playout of audio and video. So that is basically concluding the presentation here. I'm quickly skip over those slides. And now that would have been the part for questions. Unfortunately, I can't re-record the questions that we had in the audience. So that's why I forward you to some resources. If you want to learn more about timing, synchronization, 2110, PTP, AES67, please feel free to visit the resource page on the ravenna-network.com page, or the aimsalliance.org also has a resources section where you can find a lot of interesting and more detailed resources about timing and synchronization. So that's it for this presentation right now. Thank you for your attention. And if you have any particular question, you may also shoot me an email at ravenna@alcnetworks.de. Thank you for following along. Goodbye.